So this is the start of our lecture for Geo 420 on March 24th, post-COVID Zoom lectures. All right, so we talked about make sure you try and respond either via chat to everyone or via voice. I'm going to try and keep it interactive. So I am recording all these lectures and I will post them on the Moodle site. So they, you'll have access to these lectures. And the last time I did it, I've been testing all the notes that I write and everything get recorded on the Moodle lecture. So I think it should work for everybody. But I do want to try and keep it interactive, so I'd appreciate it if people logged in for the live lecture, because otherwise it's just going to be me talking, and that'll be boring for me, at least. All right. Yeah.
Can you hear me, or do I need to put my headset on? My computer.
I can hear you just fine.
Okay. The homework set, problem 1.
Yep.
Shouldn't the left-hand side be multiplied by density of water? It just has the Darcy fluxes equal mass over time. And that's what I had that multiplied by density of water in a couple places in my notes, and that's the only way I can get it to work.
Yeah, Darcy flux needs to be multiplied by water to make it mass.
Yeah, okay. So that was my question.
Okay. So problem 1 says dmdt is equal to dq dx plus dy, or dq dy plus dq dz. And Q is discharge, so you got to multiply by density to make it mass.
Okay. Thanks.
So that question reminds me, I will still, and I'll send the invite to that meeting for office hours after this. So I'll still do office hours Tuesday, Thursday from 10 to 11. And it'll be both this lecture and the office hours, I think, are just going to be the same Zoom meeting. So you just click on the same link. They're recurring meetings. And so they're just available whenever. And I'll just start the meeting and then you guys can join whenever. So I think it'll always be the same link. If that doesn't work out, then I'll have to send out a new link email each time, but I'm pretty sure that we can just use this same link for every Geo 420 lecture from now on. Yeah, so we'll do office hours 10 to 11, Tuesday, Thursday. Turning homework in, I will create an assignment turn-in site on Moodle. Oh, that's another thing. The Moodle website is going to totally change for class in that I will now have a new sort of, I guess they call them topics for each week. And that each week we'll now have recorded lectures. And then any of our in-class activities that we do, you'll turn in that week. So just expect that the interaction with Moodle, of course, will increase greatly now that we're on online delivery. Yeah, so I'll create a turn-in site for the next homework set. I think that's it. I just had Carson email me and say he can't find the Zoom link. So I'm going to forward that to him really quick. Any other general business questions people have?
How are our exams changing?
What's that?
How are our exams going to change? Are they just going to be moved to an online exam?
Yeah, we're just going to have to do them online. So I'll just have to make them double hard because I know you all cheat. I'm just kidding. We'll do them online. And yeah, they'll just be a little bit of honor code. I'll probably make them, you know, open note. That makes it worse for you guys, really. But just because not actually won't change the questions that much. You just get yourself all something worse about open note questions. I don't know. You really start to overthink it. So, and then the other thing that happens with open note questions is people say, oh, sweet, open note, I don't need to study. And that doesn't work. So at any rate, we'll address that, but it'll have to be delivered remotely. Yeah. The other thing, field trip is off. So I got to figure out how to deal with that. I'm probably going to just change the final project. Actually, I have a question for you guys. And you can maybe just text me the answers, but I'd like you to tell me what operating system computer you have, whether you have Python installed or can install Python. Well, actually, doesn't matter what operating system you have, you can install Python. But if you have Python installed, it'd be useful to know. I'm thinking of trying to get everybody to install Python and then this mod flow, and we could actually start doing some basic groundwater modeling, but it's going to require people to be able to install some software on their computers, and the complexity of that depends on your operating system. So why doesn't everybody just send me a chat response on their operating system and whether they have Python installed? And that way it'll let me mull over how I'm going to do the final project. Okay. I think that's all the business I had. Any other questions? All right. Okay, so let's get on to trying to lecture here. And so I'm going to share my desktop here. So can everybody see my desktop now? All right, good news. Okay, so one of the first things we're going to do this morning is talk about this paper by Toth that you guys were supposed to read. But before we get into discussing that paper, I wanted to just talk a little bit about regional groundwater flow and introduce some basic terminology. So first thing I wanted to do is talk about, Toth talks a lot about groundwater basins. And so I wanted to talk about some of the terminology for a groundwater basin here. So try and do some drawing here. A groundwater basin is so let's say we've got here a land surface. Now's the part where I start drawing with the computer. And put a tree on there. They're getting better. Some grass. My trees looked really bad the last couple days. It's not terrible. Okay. Okay, so here's our land surface. So there's a couple of implicit assumptions that people have made. And the first, and let's say I've got a stream down here in my valley. And the first is that the water table basically follows topography. All right, so one of our assumptions is that, that the water table is a subdued replica of topography. All right, and that's going to be important assumption for Joe's results. All right, so in general, we have a few things that we want to define here. So let's say we've got a bunch of groundwater flow paths, and they are flowing to our stream here. So these are groundwater flow paths. There's two boundaries here. All right, and these are groundwater divides. And the basic definition of a groundwater divide is that the flow paths don't cross here. The reason why there's one under the stream is that on the other side of this divide, the flow paths are coming from the other direction. All right, and we know from our flow nets that flow paths don't cross, right? So these are our groundwater divides. All right, so one of the first interesting take homes here is that there's a groundwater divide underneath a stream in general. All right, not always, but in general. There's a groundwater divide on this side because if our hill is symmetric and continues on the other side, then our water table follows it and our flow paths go the other way on this side. So we got two groundwater divides, and in between those groundwater divides is our groundwater basin. All right, so a basin is basically the area which all the groundwater discharges to a known point. All right, so we can divide our basin up into a couple different zones. So this area where groundwater is entering the system, this is our recharge zone. Oh. All right, so anywhere where the groundwater flow paths are going down is our recharge zone. All right, and then this area down here, so that's really this whole zone here is our recharge zone. And then this area and the stream where our groundwater flow paths are going up. All right, this is the discharge zone. All right, so we can break our basin up into areas of recharge and areas of discharge. And an important message here is that this zone of recharge is a lot bigger than the zone of discharge. So in general, when we think about a groundwater basin, it's most of the world is a recharge zone, and then there's localized discharge zones, usually near surface water bodies. Another important area that Joe talks about is this this zone here. All right, and that is the area where you've got basically flow paths coming from either side, but there's no flow occurring here. And this is a stagnation zone. All right, and this, so another interesting thing is that beneath a stream at some depth, you'll get these stagnation zones where you have really old water that's just not turning over because the water is circulating on either side and not flowing through this area here. There's also stagnation zones here and over here. All right, so these are some of the terminology that are important to think about when you read the Toth paper. All right, so the main take-homes, water table is a subdued replica of topography, large recharge areas, small discharge areas, and then we have stagnation zones where the groundwater doesn't really flow anymore. Okay, so the next thing I wanted to do was have you guys talk about your talk about the paper and I want to try doing some breakout rooms. So here's what I want you to do. So on the Moodle site, and I'm going to throw it up here on my computer, is some questions that I want you to answer about the Toth paper. So on the Moodle site, you can get these questions as well. And I'm going to break you guys. So there's 9 people. So I'm going to break you guys into 3 breakout rooms. I don't know what's going to happen now. So we're about to enter the unknown. What I'm hoping, I think it's supposed to break you guys into 3 rooms automatically. And that each room is sort of its own meeting. And so what I want you guys to do is I'm going to give you 15 minutes. If you haven't read the Toth paper, then you need to skim it. And I want you guys to discuss the answers to these questions here that I want you to answer about Toth's paper. And I'm going to delete some of this space here so all the questions can be on my screen at once. All right, so before we start with the breakout rooms, a little help if you're not used to reading research and scientific literature papers. So this one, it's a little different because this one's a little older. And so it's amazing how much the styles of writing have changed over the years. But in general, the abstract is supposed to give you a quick summary of the entire results of the paper. All right, and so it should tell you what they did, what the main results are, and the implications. Joe doesn't really give you many methods in his abstract, so this is before abstracts were supposed to contain methods, but it does give you the basic results. So the first thing you do is read the abstract well. The introduction is supposed to give you enough background to know why this is an interesting problem, and then tell you how they're going to address this problem. All right, and then you should get into methods after that. All right, so this paper is actually a really quick read. It is, 16 pages long, and most of these are full plate figures. All right, so even if you guys didn't do the reading, you should be able to skim it and get most of these answers from the reading pretty quickly. Okay, so let's try going to breakout rooms. If it doesn't work, just text me, and we'll go from there. All right, I'm going to try it. How did it work? Is it working?
where it had the breakout, and then everything goes around it.
How's
Stagnation
the
zone goes
breakout
on.
going? Is it working?
Yeah,
Yeah.
so far.
We are breaked out, so yeah, it is. Besides it being Zoom,
Peyton, can I hop between rooms like you can?
No, man. That's special powers.
only for God. I see.
Yeah.
I see how it is.
Special powers.
Uh,
All right. Sweet. I'm going to go check out another room. See you guys.
okay.
Peace.
How's the breakout room going, guys? Is it working?
Yeah, we're trying to load the questions on Moodle, but at least my computer is being incredibly slow.
Yeah, and you probably can't see my screen anymore.
No, we can't.
Okay, let me see if I can send out a file. I will I didn't think about that. All right, let me I'm leaving and I'm on it. See ya.
Okay.
All right. Oh,
So did it send you guys like a message to leave the room? Yeah.
yeah, and a button we could click because it would auto do it, or we can click it.
Okay.
Yeah.
Cool. That actually worked pretty smooth, I think.
Yeah.
Zoom is continues to impress. I haven't had much issues. We'll see whether they can handle all the bandwidth, but so far so good. Okay, so I think that worked. I'm going to share my screen again. So are you guys seeing my screen again?
Yes.
Okay. And
Are you currently using two screens?
I have two windows up, but just one screen.
Okay.
Why? What's up?
I was just saying I was seeing both of them. I wasn't sure if you're wanting me to both see the paper and also what you're writing on.
Yeah, I want you to see the paper because I can do all kinds of fun stuff now. Draw on the paper.
Oh, I'm so excited.
It's freaking high tech over here, man. All right. So, but I do like to see the chat window, so I got to figure out how to get that going. Okay. All right. Okay, so let's talk about a few things about this Toth paper. Well, the first thing that I wanted to discuss is that, you know, what Joe's doing here is he's solving a boundary value problem. And in particular, he's solving the groundwater flow equation for a certain set of circumstances. So, you know, my first question here was, what was his domain of interest? So what sort of domain was Joe looking at here?
Well, he talked about the local, intermediate, and regional basin sizes, but places emphasis on the small because you can upscale from there. And then did it for like 3 different depths of sediment regimes, I guess.
Sure, agree with all of that, but in general, when I think about the domain of interest, it's like what? So all of that was very true and very right. He is thinking about flow in sort of in a basin, and he has this idea of a small drainage basin of different depths. But what domain did he solve the groundwater flow equation in? So here, this is actually like, what was his simulation domain? So you can get that by looking here at figure 1. So he's simulating it on an idealized cross section of a valley flank. And really what he's looking at 2-dimensional flow in a rectangle. All right. So this is his domain. So Joe's domain is a rectangle. All right. And all right, were you guys able to see what his governing equation was?
Yeah, it was ugly.
Well, the actual governing equation was not. So
Yeah, it was just a 2D Laplace per head, right?
yeah, this is it right here. So here's the governing equation. Oh, well, let me highlight it. And it's this guy here. It's the Laplace equation for head.
Oh, it wasn't number 6?
Number 6 is
All the way down the bottom of that page.
That's a solution.
Number 6 is the solution, the analytical solution. So he solved this governing equation. D squared. I'm going to use our nomenclature. Dx squared. And he does use z plus d squared h dz squared equals 0. All right, so just from this equation, you should be able to look at this and tell me some things about his groundwater flow system. So what can we tell from this governing equation about his groundwater flow system?
First of all, it's a steady state.
Right. So steady state.
It's homogeneous and isotropic.
Yep. So steady state, homogeneous, and isotropic. All right. So simple. Steady state, homogeneous, and isotropic. All right.
Could you also say confined, or is that something else? Confined and transient?
You could say he's doing a trick here. You could say that the thickness doesn't change. And after we talk about the unconfined groundwater flow equation, you can see how I know that. But the reason why is, so what he's done is he's simulating on this block. So the next question is, what are his boundary conditions? So he has to assign conditions on all parts of this boundaries of this block. So what are the boundary conditions he assigns?
Defines an impermeable horizontal boundary at its base.
All right, so this guy is no flow.
And then so are the
And-
two vertical boundaries. which slope
Subvertical,
downward.
is it?
Yeah.
Subvertical,
No flow.
And a constant level water table is assumed.
Yeah, so let's talk about the water table in a sec. But agreed, it is constant. All right, so no flow at the base. I could see, all right, at some point there's an impermeable layer, that's fine. How did he get these no flow boundaries on the two sides? Why would that be reasonable?
I guess on the left side, he's assuming that's where the river is at, and that the flow paths do not cross underneath the river. That's where they're all discharging into.
Yeah, so what did we call that? A
Stagnant.
groundwater divide.
Yeah, and then
At the
same
stream,
thing.
and a groundwater divide at the upstream side.
at the elevation, the higher
Yeah,
elevation.
so
So all
that's
of the
our
flow,
groundwater basin is divided by our groundwater divides, which are no horizontal flow. We don't get flow across them. All right, so now the next thing is this top boundary condition. And this is where what Joe did really changed the way we think about groundwater flow. So this guy, so the first thing he did was say, all right, there was, in general, we have always talked about there being sort of a constant sloping water table, right? That's following this sort of constant line. And he said that was at this angle alpha. So this guy, this line would be given by H is equal to X times tan alpha. Actually, let me erase this. Looks terrible. So this line is H is equal to H naught plus tan alpha times X. All right, so that's just an equation for the height of this line above this level H naught. All right, and then he said, but on this regional slope, so this is some regional slope like going up the Great Plains, all right, which is where Joe worked. He worked on the Great Plains out in Alberta, all right? And he said superposed on this slope, say along the Great Plains up to the Rocky Mountain front, we have undulating topography of a smaller wavelength, right? And so on top of this was this sine wave, all right? And we could characterize this sine wave as having some wavelength, 2 pi over the frequency, all right? And some amplitude, this distance, A, which was the height of our wave, or the basically A is the amplitude or the height of the topography, of the local topography. All right, so our topography really gets characterized here by two parameters, the wavelength, so how rapidly the topography is changing, and the amplitude, that is the height of the change. All right, so let's talk about boundary and initial conditions. Oh, we talked about boundary conditions up there. What about initial conditions? Does initial conditions make sense for a steady state problem?
No.
No, they don't, because it stays at the same condition all the time. So we don't need to worry about initial conditions. What about subsurface parameters here? So hydraulic conductivity, storativity, things like that. Do we need to worry about that with this governing equation?
No, because there is no, the hydraulic
Yeah, they fall
conductivity is the
out.
same in all, yeah, it falls out and it's the same in all directions.
Right, so we don't, since it's homogeneous and steady state, we don't need to worry about it. So our life gets way better when we have a homogeneous steady state system. Okay, so now I want to talk about the major conclusions and impacts or implications of Toth's results. So first of all, the main thing I want to say is, okay, this ugly equation that Mark talked about, this equation 6, all right, this is his analytical solution, all right? So this is his analytical solution, and by analytical solution, we mean it is a function that gives us the head, all right, at any location. So what we need to give it is the height, and for any location, we can determine the, so for any x and any z, all right, we can determine the value of head. All right, so this is an analytical solution. It follows this governing equation subject to these boundary conditions, all right? And the result is a function, this nasty function, but it gives us the value of the head at any location x and z in our domain, all right? So these analytical solutions are gold. They give us head at any place in our domain, all right? And allow us to solve for the groundwater flow, but we can only derive analytical solutions for very specific cases and simplified cases. So in this case, it works because we were steady state and homogeneous and isotropic, all right? And we were able then to derive this analytical solution, but you can see that even for this very simple system, our analytical solution is messy. All right, so this is an analytical solution, and we can use it to look at the groundwater flow paths or flow systems. What's going on here? It's just turning them upside down. The one I really wanted to focus in on that sort of summarizes it all is this guy here. All right, so here is, I would call his sort of basic fundamental results figure. And the main take homes that change the way we think about groundwater after this paper was written were a couple things. The first of all is that we had these nested flow systems. So we have these shallow local flow. And then we've got this deeper regional flow. And in between, we've got this mysterious intermediate flow. And no one ever really knows what to do about intermediate, how we define it, what it really means. In general, most groundwater hydrologists break it up into two things: the local flow system and the regional flow system. And the big thing about, so there's a couple important points. The local flow system is basically following the local topographic divides. All right, so this is your surface watershed. So water would drain to this low point here if it was rain. And the local flow system follows the surface watershed. So this follows your surface watershed. But our regional flow is going from one high point and skipping a bunch of the local discharge zones and going all the way to another disparate discharge zone. And it says that a groundwater basin is not equal to the surface water basin. All right, and that's an important point. We can have watersheds up high, and these guys are net water exporters. All right, they are not moving all the water to the adjacent stream. Some of that water is leaving the system and discharging to another stream in another watershed. All right, so this one is a water importer. This watershed would have a water surplus that is fed from water in a very different and disparate surface watershed. So this idea of nested groundwater systems, some of which are short flow paths, shallow flow paths, following the surface watershed, and some of which are deep regional groundwater flow paths that don't follow the surface watershed. This really forced groundwater hydrologists to rethink the way we conceptualize groundwater flow systems, and for surface water hydrologists to think about this process as well. How do these regional flow paths impact their surface water budgets? We can think also about, so these surface watershed, these surface or local flow paths are much shorter and much shallower, and they are more susceptible to drought. They're more susceptible to contamination. All right. They have residence times. These things, flow paths are usually 1 to 10 years here. These regional groundwater flow systems, pretty impervious to drought. Or even climate change, and to some extent less impacted by contamination. And they have residence times, you know, on the order of 100 to 1,000,000 years. All right, so you can imagine, I've worked in some of these regional groundwater systems where the age of the water where it was discharging to the river was like, you know, 500,000 years, 500,000 years. It doesn't care about any kind of climate change, all right? On the order of 10,000 years. This thing is 500,000 years old down here. It is impervious to whatever's happening to the climate. But this thing, you know, it's refreshing itself every 1 to 10 years. It really does matter what the local climate is and what the climate is at that time. All right, so the main things I wanted to, the main take homes from this Toth paper, the first and most important one is that we can expect groundwater flow to have this nested set of scales from local to regional. All right, and that should be the expectation of groundwater hydrologists, not the exception. And that our stream, especially our higher order streams, are receiving discharge from flow paths of a variety of different lengths. Everything from, so this stream here, it's getting local flow, it's getting regional flow, and it's getting intermediate flow. So it's getting this broad distribution of flow paths. Our higher order streams are only receiving local flow, all right? There were some other important sort of nuances to this result that Toth was able to get back or investigate, because once he had his analytical solution, he could do things like test. So with my analytical solution here, I can do things like test the effect of the topography. So I can test, this was my frequency of my wavelength. This was the amplitude of the wavelength. All right. With these two, I can test, well, what happens if I have really big undulating topography? All right. What happens if I have really long wavelength topography or really short wavelength topography? And we can start to think about the situations where we might expect regional flow to dominate versus local flow to dominate. All right, so some of the basic take homes from Toth's paper are this. All right, if we have no local relief or small no or small local scale relief. So if it's flat, all groundwater is regional. All right, so the caveat to that is local flow develops when we have topography. Higher relief means more local flow. And deeper local flow systems. All right, the fluid velocity, so the groundwater discharge is greater in local flow than regional. And the majority of groundwater discharge will be from local flow paths. The caveat here is these are more impacted by climate and drought. Climate/drought and contamination. And these regional flow paths, it's a low amount of discharge, but it's constant and really not impacted by climate. All right, so Toth's paper really changed the way we think about groundwater flow. It opened up this idea of nested flow systems. So the next paper that I'm gonna give out, I'll send it to you guys after we're done lecturing here, is a follow-on to Toth. And essentially, it's a paper where they use a numerical groundwater model to model more complicated situations. So the caveat to all of these is that this is homogeneous. And it ignores geology and heterogeneity. So the next paper we're going to look at is really the next step, where we explore the effect of heterogeneity. Amanda, did you have a question?
I do have a question. I don't know if it's related, but thinking about the differences in resiliency between regional and local.
Yep.
Are they susceptible to changes in topography? I know generally like those are on much larger time scales, but like thinking of like Mount St. Helens, is that that sudden change in topography, does that affect them both the same way or differently?
Yeah, so a good question. So in general, regional flow would tend not to be too susceptible to changes in topography because these are flow paths that have been set up by like large wavelength topography, like the fact that the Rocky Mountains are there, not the shape of Mount St. Helens, but the fact that Mount St. Helens is higher than all the surrounding valleys. But the local flow systems could get very affected by it. So, you know, in that case, if you blow off half your mountain in a volcanic explosion, then all those local flow paths got totally changed by the new topography. Okay. Any other questions about Toth's paper? All right, so I'll send out the Freeze paper. Comes out a few years after the Toth paper, and here we're going to look at two things. One is the effect of heterogeneity, so we'll look at the science result, but also the other super important part of the Freeze paper is that it's one of the first computer numerical solutions to the groundwater flow equation. Maybe the first that was published. And now the whole industry, if you do groundwater science, you do numerical models.